Gases. They're all around us. But what exactly are they? Gases are substances that are normally in the gaseous state at ordinary pressures and temperatures. They have the ability to fill out their containers, but are not confined to the container's volume by gravity as liquids are. To describe the gaseous state, 4 quantities are needed: the quantity of gas in moles, the temperature of the gas in kelvins, the volume of the gas in liters, and the pressure of the gas in kilopascals. Gas molecules are in constant motion, colliding with each other and with the walls of their container. These impacts cause gas pressure. The pressure of a gas is a measure of the force it exerts on its container. Pressure can be found using a simple equation: force divided by area, or newtons per square meter. 1 newton per square meter is known as a pascal. A barometer is any device that is used to measure the Earth's atmospheric pressure. A mercury-filled barometer is made by inverting a column filled with mercury in a mercury dish. Some of the mercury flows out when the tube is inverted. The space in the tube above the mercury is nearly a vacuum. Only negligible amounts of mercury vapor occupies it. At sea level, the height of the mercury column is about 760 millimeters above the surface of the mercury in the dish. The pressure of the atmosphere on the surface of the mercury in the dish is balanced by the downward pressure exerted by the mercury in the column. 760 millimeters of mercury is the same as 1 atmosphere, which is also the same as 101.325 kilopascal. Pressure of gases is measured by an instrument called a manometer, whose principle of operation is similar to that of a barometer. Closed-tube manometers are used to measure pressures below atmospheric pressures. The pressure is simply the difference in the heights of the mercury levels in the 2 arms. Here, since the 2 arms are at the same level, the mercuric pressure is 0. Here, since the left arm is higher by 40 millimeters, the pressure is 44 millimeters mercury. An open-tube manometer is an instrument used to measure gas pressures that are near atmospheric pressures. The difference in the heights of the mercury levels in the 2 arms of the manometer relates the gas pressure to the atmospheric pressure. If the pressure of the gas in the bulb is the same as the atmospheric pressure, then the levels of the 2 arms are equal, and the pressure is hence the atmospheric pressure. If the pressure of the gas in the bulb is greater than the atmospheric pressure, then the mercury will be forced higher in the arm exposed to the atmosphere, and the pressure is the atmospheric pressure in millimeters mercury plus the height difference. If the atmospheric pressure is greater than the gas pressure, the mercury will be higher in the arm exposed to the gas, and the pressure is the atmospheric pressure in millimeters mercury minus the height difference. Experimentation in the 17th and 18th centuries led to the understanding of gas behavior and to the formulation of important gas laws. Let's start off with Boyles Law. When the pressure of the gas is plotted against volume, we observe a nonlinear function. When the pressure of gas is plotted as a function of 1 over v, a straight line is observed. This type of plot demonstrates that the volume and pressure of a gas are inversely proportional. They change in opposite directions. Here we have a balloon. Little Kalvin here loves playing with his balloon. One fun activity he likes to do is squeeze his balloon for reasons that are unknown to us. As he presses into the balloon, he's actually lowering the volume of the air, and the pressure inside of the balloon increases. Kalvin notices this when the balloon gives resistance to his squeezing after a certain point. Be careful, Kalvin. You don't want your balloon to pop. Mathematically, we can write this in 2 ways. This is such that the number of moles and the temperature remain constant. Both of these relationships show that for a fixed mass of gas at a given temperature, the gas volume increases if pressure on the gas decreases, or conversely, if the pressure on the gas increases, then its volume decreases. Thus, we know that P times V remains constant for the same gas. Therefore, we can say that the product of P and V remained the same for the same gas. When he filled up the balloon, the pressure of it was 81.06 kilopascal, and the volume was 750 milliliters. After doing some research, Kalvin found out that the balloon he was playing with pops at 207.7 kilopascal. At what volume will the balloon pop when Kalvin squeezes it? In order to solve this problem, Boyles' Law would need to be employed. Next, we'll move on to Charles' Law. When the volume of the gas is plotted against temperature, a straight line is observed. This plot demonstrates that volume and temperature are directly proportional. Note that if we represent the temperature in degrees Celsius, the line does not pass directly through the origin. If we extend the graph to the left, we notice that the temperature when the gas's volume is 0 is negative 273.15 degrees Celsius. This is known as absolute zero and is 0 on the Kelvin scale. That is why we always measure temperature in Kelvin for calculations in chemistry. Thus, 0 Kelvin is negative 273.15 degrees Celsius. Little Kelvin's back. His parents, Gabe and Chrisella, are taking him to the beach to beat the heat. Kelvin brings his balloon with him. When he gets there, he realizes that the balloon seems fuller. How can it be? Well, using Charles' law, when he brought the balloon to the beach and it was exposed to the higher temperature, the volume of the air inside the balloon increased as well, making Kalvin a happy boy with a happy balloon. Kalvin was so happy that he named his new best friend Balloony. Mathematically, we can write the relationship like this. This is such that the number of moles and the pressure remain constant. Both of these relationships show that for a fixed mass of gas at a given pressure, the gas volume increases if temperature of the gas increases, or conversely, if the volume of the gas decreases, then the temperature decreases as well. Thus, we know that V over T remains constant for the same gas. Therefore, we can say that the quotient of V and T remain the same for the same gas. When Kelvin filled out his balloon at home, the temperature was 23 degrees Celsius and its volume was 875 milliliters. After arriving at the beach, he found out that the balloon had expanded in size to 910 milliliters. What was the temperature at the beach in degrees Celsius? We can find out the answer using Charles' law. Let's move on to our third law, or the Gay-Lussac law. When the pressure of the gas is plotted against temperature, a straight line is observed. This plot demonstrates that pressure and temperature are directly proportional. Kelvin's been having a rough day. The bully, Chu Chang, pushed him into a snowbank at school. Luckily, Kelvin knew that he could always count on his best friend, Balloony. He took Balloony outside to watch snowflakes, but started noticing that Balloony was shriveling up. He panicked, but then remembered the wise teachings of his teacher, Miss Pavita Sall. She told him about the Gay-Lussac law, which explained why the low temperature led to lower pressure in the balloon and its shriveled appearance. Kelvin went inside to get a warm cup of cocoa, and Balloony was back to normal in no time. Mathematically, we can write this relationship like this. This is such that the number of moles and the volume remain constant. Both of these relationships show that for a fixed mass of gas at a given volume, the gas pressure increases if temperature of the gas increases, or conversely, if the pressure of the gas decreases, then the temperature decreases as well. Therefore, we can also say that the quotient of P and T remain the same for the same gas. Kelvin's balloon's initial pressure was 96.26 kilopascal when he filled it up in an environment with a temperature of 24 degrees Celsius. When his balloon shriveled up, the pressure inside was 84.3 kilopascal. What was the temperature outside? This is a question that can easily be answered using the Gay-Lussac law. Next, let's move on to Avogadro's law. When the moles of gas is plotted against its volume, a straight line is observed. This plot demonstrates that mass and volume are directly proportional. Kelvin and his balloon had been through everything together, but as time went on, Balloony slowly lost that spark that had ignited their friendship. His father recommended refilling Balloony with more air, and Kalvin obliged, desperately hoping to repair his broken relationship with Balloony. He also knew that if his father increased the amount of air in his balloon, Balloony would regain her volume, thanks to Avogadro's law. His father completed the air implant, and Kalvin and Balloony rekindled their love again. Mathematically, we can write this relationship like this. This is such that the pressure and temperature remain constant. Both of these relationships show that for a fixed temperature of gas at a given pressure, the mass of the gas increases if volume of the gas increases, or conversely, if the mass of the gas decreases, then the volume decreases as well. Thus, we know that V over N remains constant for the same gas. When the balloon was at its lowest point, its volume was 0.53 liters, and there were 0.0441 moles of gas molecules in it. Knowing that the father had implanted the balloon with 0.049 moles of gas molecules, what is the new volume of the balloon? Let's turn to Avogadro's law to find out our answer. When we combine the four gas laws, we obtain the general gas law, also known as the combined gas law. Remember, this equation only applies to the same gas. Now let's talk about the ideal gas law. Knowing that volume is proportional to pressure, temperature, and number of moles, combining these three relations gives us another proportionality statement, written as volume being proportional to number of moles times temperature divided by pressure. This relation is equated by the constant R. By rearranging the formula we can derive our beloved ideal gas equation, PV equals nRT. The value of the constant R is known as the universal gas constant, with a value of approximately 8.314. We also know that the number of moles is mass divided by molar mass. Thus, we can rewrite the ideal gas equation like this. We also know that density is equal to mass divided by volume. By substituting this into the previous equation, we obtain this. Let's move on to STP. Standard conditions for temperature and pressure, or STP, is at 273.15 Kelvin and 100 kilopascals, while standard ambient conditions for temperature and pressure, or SATP, is at 298.15 Kelvin and 100 kilopascal. Molar volume is the volume occupied by 1 mole of gas at STP. By substituting the values of STP into the ideal gas equation, as well as 1 for the number of moles, we obtain a volume of approximately 22.7 liters, or the molar volume.